The title of my presentation is Comparative Study of Enzymatic and Chemical Denaturation of Wheat Gluten and their Cellulosic Nanocomposites. This study is a part of the project entitled Protein-Based Nanocomposites for Food Packaging between the Academy of Scientific Research and Technology in Egypt and Campus France. The objective of the project, of the whole project, is to develop food packaging materials from cheap, biodegradable, and renewable resources. And now, what is the problem? The problem is that the majority of packaging materials are non-biodegradable, which do not meet the demands, the increasing demands in society for sustainability and environmental safety. But numerous biopolymers have been exploited to prepare food packaging materials. The usage of these biopolymers has been limited due to the poor mechanical and barrier properties when compared to non-biodegradable materials derived from petrol. But these properties can be enhanced in several ways. The specific objective of this study or this presentation is to examine the role of nanocellulose, whether cellulose nanocrystals or cellulose nanowhiskers or microfibrillated cellulose as a reinforcing agent on the chemically and enzymatically denatured wheat gluten films. In this study, we used two biopolymers, cellulose and wheat gluten. It's well known that cellulose is the most abundant biopolymer used on Earth. Cellulose consists of glucose units linked together with cellulose consists of glucose units linked together with 1,4-beta-glucosidic linkage. Each glucose unit possesses 3 hydroxyl groups. These hydroxyl groups are the key for functionalization and modification of cellulose, and they are the basis for the extensive hydrogen bonding network responsible for the character of cellulose, which is a semi-crystalline fibrous material. In our lab, we worked on nanocellulose, cellulose nanocrystals, or microfibrillated cellulose since 2008. Here is the microfibrillated cellulose prepared from the agriculture waste bagasse, which is sugarcane bagasse and rice straw. Its dimensions are from 2 to 10 nanometer width and several tenths of microns length. Microfibrillated cellulose prepared by, as said before, by mechanical treatment. The benefit is that no chemicals used for this preparation of microfibrillated cellulose, but it's energy consuming. Also, we prepared nanocrystals or cellulose nanocrystals also from bagasse and rice straw. It's prepared by hydrolytic cleavage or acid hydrolysis. The hydrolytic cleavage works on the cleavage of the glucosidic bonds, releasing the crystalline part of cellulose. The second biopolymer used is wheat gluten. Wheat gluten is a protein. It's a byproduct due to production of starch from wheat. Wheat gluten consists of two main proteins, glutenin and gliadin. Gliadin with lower molecular weight, ranging from 15,000 to 80,000, and the glutenin with higher molecular weight from 80,000 to maybe millions. This is the molecular weight of glutenin. Generally, plant protein needs a process named denaturation. Denaturation of plant protein is essential process for processing of protein. Protein is insoluble in water, so denaturation causes unfolding for the protein chains to expose the hydrophobic zones in the chains for reactions. Denaturation may be heat, chemical denaturation, enzymatic denaturation. In our study, we use the chemical denaturation and the enzymatic denaturation. The chemical denaturation part was published in Carbohydrate Polymers. This part was published under the title Development of Wheat Gluten Nanocellulose Titanium Dioxide Nanocomposites for Active Food Packaging. We prepared wheat gluten films filled with cellulose nanocrystals with different percentages and titanium dioxide. And we characterized the prepared films by scanning electron microscopy, and the water sensitivity was also characterized by contact angle, water vapor uptake, water vapor permeability. The mechanical testing was characterized by tensile strength and Young's modulus, and also the antimicrobial activity of the films was determined. The electron microscopy of the prepared films shows the homogeneity of the films, and filling the wheat gluten films with higher percentages of cellulose nanocrystals results in aggregation of the result of the third one. The water sensitivity of the prepared films was characterized by, firstly, by contact angle. We can see that filling the wheat gluten films with cellulose nanocrystals and titanium dioxide results in more hydrophobic surface. Hydrophobicity of the films is necessary character for films used for food packaging. Water vapor uptake was investigated under the worst conditions, under 98% of relative humidity. We can see that filling with cellulose nanocrystals and titanium dioxide resulted in lower vapor uptake due to the network of the resulted from hydrogen bonding of cellulose nanocrystals and the amino acids or the amino groups constituting the chains in the protein. Also, water vapor permeability showed not significant enhancement, but it's less than the control one. The mechanical properties of the prepared films showed significant enhancement of the tensile test, and also decreasing of the elongation at break due to filling the films with cellulose nanocrystals and titanium dioxide. Where is the pointer? We also know that paper is the most popular bio-based material for food packaging, but its water permeability and being a good media for microorganisms growth are the drawbacks for using paper in food packaging. Coating of paper, usually coating of paper with plastic or aluminum foil is a good solution, but water will lose its biodegradability when it's coated with plastic and aluminum. So, coating of paper with biopolymers in this study was a good solution to increase its antimicrobial activity, to increase its mechanical properties. We chose the last solution consisting of wheat gluten, cellulose nanocrystals, and titanium dioxide to coat commercial paper with 1 layer, 2 layers, and 3 layers. The coated paper was exposed to UV light for half an hour, 1 hour, and 2 hours. And this table shows the colony forming units and the reduction percent of the surviving number of the tested bacteria. We used yeast, S. aureus bacteria, which is gram-positive bacteria, and E. coli, which is gram-negative bacteria. The results of yeast is not shown in this table because complete inhibition of the yeast was achieved after half an hour of exposure of the paper to UV light. Regarding the S. aureus bacteria and E. coli, nearly complete inhibition was achieved on exposure of the coated paper for 2 hours to UV light. It is 98% inhibition and 100% inhibition of the S. aureus bacteria after 2 hours of exposure to UV light. Regarding the second part, which is enzymatic denaturation of wheat gluten, we used the alkylase enzyme. The doses of the enzyme used was 0.5, 1, and 2. Our parameter here, which conditions will result in the higher solubility of the wheat gluten. We found that the higher solubility was obtained maybe for 1% alkylase enzyme after 8 hours, the conditions used. Wheat gluten, which is enzymatically denatured, was filled with cellulose nanocrystals, which was used in the first part by chemical denaturation. But unfortunately, the films were loose and we didn't use cellulose nanocrystals in this study of enzymatic denaturation of wheat gluten. We used microfibrillated cellulose. Microfibrillated cellulose here filled chemically and enzymatically denatured wheat gluten. The dark blue for the chemically denatured wheat gluten, and the pale blue for the enzymatically denatured. They were filled with percentage of microfibrillated cellulose till 30%. As we can see that chemical denaturation was more better than enzymatic denaturation. I think that the hydrolysis of the wheat gluten resulted in low molecular weight wheat gluten, which was unable to make good film, and the chains did not arrange it in good manner to produce good films. And the chemical denaturation was better. Also, the water vapor permeability, comparison between the water vapor permeability of wheat gluten denatured and chemically denatured, and also the chemical denatured showed less permeability, which is better than the enzymatic denaturation. Contact angle measurements was also didn't result in hydrophobic nature like the chemical denaturation. The scanning electron microscopy of the enzymatic denatured wheat gluten filled with microfibrillated cellulose. The films were homogeneous for the low percentage of microfibrillated cellulose, and 30% of microfibrillated cellulose resulted in aggregation also in the prepared films. We can conclude that filling of chemically and enzymatically denatured wheat gluten with microfibrillated cellulose enhanced the mechanical and barrier properties of the prepared nanocomposites. However, this enhancement is significant in case of chemical denaturation, especially for microfibrillated cellulose content more than 15%. Also, attempts to develop thermoplastic films from wheat gluten to replace synthetic biopolymer-based films need more extensive studies to achieve the target. finally, I would like to acknowledge my colleagues, Dr. Ines and Dr. Ragab. And also, we acknowledge the Academy of Scientific Research and Technology in Egypt and the Grenoble Institute of Technology for their financial support. Thank you.
Questions? Any question?
Oh, okay.
Thank you. It's very interesting presentation. One of my questions is you tested comparing with the chemical treatment with the enzymatic treatment. But when you treatment with enzymatic treatment, you just apply the... Yeah. And you say the chemical treatment is much good result compared to the... And it's better, is right? Yeah. But your working condition applied the enzymatic treatment is only you 2%, 1%, 0.5% applied. But don't you think if you apply some more variety of the condition applied, maybe you can optimize some enzymatic application condition, so can it pretty much compare to the chemical treatment? Don't you think so?
You think that I must continue the enzymatic?
Yeah, I guess maybe.
I must continue the application for the enzymatic and apply the solution formed on paper for more precise comparison. Yes. The films prepared were not like that one prepared by chemical denaturation. You know, the chemical denaturation resulted in good mechanical properties and improved the water sensitivity. This is not the case for enzymatic denaturation. I don't think that the application of the enzymatic denaturation with gluten on paper will result in better results for the application. No, there is great difference between the films prepared by chemical denaturation and enzymatic denaturation. Even the contact angle, which is a measure of the hydrophobicity of the prepared films, it's 80s in chemical denaturation and 40s and 30s for the enzymatic denaturation. It's a great difference. So when you apply this on paper, I don't think that good results will be obtained when you apply this enzymatic denaturation on paper. Okay.